Assalamualaikum. My name is Nur Haini and I'm going to present the review of electrical conductivity bamboo biochar for energy storage application. So for the introduction, due to their higher energy density, electrochemical stability, large evidence and safe operation, biowaste material which are mainly composed of carbon are being extensively studied as capacitive electrode. Recycling carbon from biomass is an effective way to generate alternative energy sources, as it not only protects the environment by reducing pollution, but also generates green energy, which is widely used in energy storage system. Since bamboo is widely used in the worldwide, and the bamboo fibers have a highly porous microstructure, the bamboo has recently attracted much attention recently. So, for the problem statement for this study is large quantity of forestry waste, which is biomass, are generated. So, conventional kilns are often used to manage this waste, but they are not very effective and rarely produced. The feedstock and its property, such as pyrolysis system, temperature, and residence times, are some of the factors that influence the production and quality of biochar. Hence, it is still very difficult to optimize these variables to create the best condition for biochar production and quality. So the next significance of this study is to produce biochar as a commercially viable bioproducts that support bioeconomy, that refers to the process of discovering and utilizing biosources, which involve the application of biotechnology to produce new and economically viable bioproducts. So, the objective for this study are to identify comparative analysis of the electrical conductivity properties of different types of biochar and to determine the optimal combination of properties that enhance the quality and performance of bamboo biochar in energy storage application. So, without further ado, let's take a look at the literature review about carbon properties for energy storage application. Biomass feedstock has gained popularity as a source for carbon nanomaterial preparation due to its outstanding properties, including high tensile strength, big aspect ratio, high thermal and electrical conductivity, and low density. The main differences between carbon black, activated carbon, and biochar are shown in Table 1. Although they both have evidently porous amorphous carbon matrix, biochar and activated carbon are not fundamentally different from one another. One could even consider material made of activated carbon from biochar to be essential biochar, but the main difference between activated carbon and biochar is that the former's surface is typically evident in the functional groups. Biochar made from agricultural waste has a high carbon content, which enhances the electrode's material overall conductivity and facilitate effective electron transport during the charge-discharge process. According to the source and processing parameters, lignin-derived biochar can be produced with characteristics similar to carbon blacks, such as tiny molecule size, strong electrical conductivity, and considerable capacitance. Recent research indicates that a range of biochar-based materials with supercapacitive qualities comparable to commercial activated carbon materials can be created by pyrolysis or hydrothermal treatment when combined with activation techniques. Although biochar is naturally porous, similar to its biomass precursor, electric conductivity of monolithic biochar is controlled by electrons that only pass through the rigid carbon matrix. As a result, denser biochar should have higher bulk electrical conductivity because their raised density lowers the insulative composition of their non-conductive air-filled holes in the main structure. Table 2 display the 3 carbonized biochar sample at 1000, 1250 and 1500 degrees Celsius were tested for bulk electrical conductivity, bulk density, and porosity using a modified tube two probes oriented in an axial direction. So table 2 shows that balsa biochar has the smallest bulk electrical conductivity value and was 10 times smaller than African ironwood biochar, and the bamboo biochar had the highest bulk electrical conductivity out of the biochar studied at all the process of carbonization temperatures. Furthermore, measurements along the axial direction were made for the conductivity values found in the study. Because of their anisotropic anatomical characteristic, wood and others biomass charcoal exhibit higher electrical conductivity in their axial direction than they do along their radial or tangential direction. Next, in figure 3, the 5 samples conductivity having quantifiable values is plotted in relation to their carbon content as shown in table 3. The conductivity of this sample ranged from 5 to 400 S per m, and their carbon contents range from 83 to 95 weight%. Clear that degree of carbonization of biochar has significant impacts on its conductivity. An additional few percent more carbon can significantly increase conductivity. This conclusion makes sense since an insulator is dry wood, which is a blend of organic polymer, yet if the atoms in the carbon has a sp2 electron configuration as they do in graphite and graphene, then carbon can conduct electricity. Nevertheless, the sample with the highest conductivity SM6 was not the ones with the greatest carbon content, indicating that the biochar's conductivity is also influenced by other factors. Remarkably, the conductivity ranking appears to be in line with the O per C and H per C atomic ratio, but in opposite order. Hence, conductivity decreased as their ratios increase. So, for conclusion, bamboo biochar has largest graphite nanocrystal size that is significant of precursor cellulose concentration and graphitization for electrical conductivity, and bamboo-derived cellulose was thought to be one of the most promising sources of cellulose that shows several encouraging results in energy storage applications, which are high capacitance, high energy density, and good cycling stability. However, to improve the bamboo biochar's performance, takes into account the following suggestions. The first one, incorporate conductive materials into the biochar matrix to significantly higher conductivity. Next, using composite material by combining with biochar matrix with conductive polymer or metal oxide to leverage the high surface of biochar to increase the number of active sites for electrochemical reaction, enhancing the capacity and energy storage capacity. And lastly, optimize the carbonization process parameters such as temperature, heating rate, and duration to maximize the formation of graphitic carbon structure with their biochar. So that's all from me. Thank you for watching.